Hi, this is Jacob White, and this is my Lab 4 presentation. So, Introduction to Lab. In this lab, we're going to simulate different configurations of circuits. The purpose of this is to calculate values such as resistance and current using the loop rule and the node rule to solve for unknown variables in the circuit. The circuit systems were simulated on a Java program that allows the user to create circuits that mimic real life while also providing tools such as the voltmeter and ammeter to measure potential difference in current. And then for the results, I was able to accurately model two different circuits as our experimental values matched up with values calculated from the loop and node rules. I obtained a final result of 5.998 for the time constant of the RC circuit. So here's the fundamental physics used, including the loop node rule, the conservation of energy, and then the potential difference. So here's the first circuit system. So you can see that both ammeters read 0.02 amps, which is in line with my predictions from the loop rule. And when flipped, the ammeter still reads 0.02 amps. And then here you can see the values of the circuit. So then and this one is broken, so the ammeter reads 0 amps because the circuit is disconnected. But the voltmeter reads -3 volts because this is the potential difference that is created by the battery. So in this, we're measuring the potential difference of each piece of the circuit. And then so summing up the potential differences from each piece, we get 3 volts plus -0.959 volts plus -2.041 volts equals 0. So this result is in line with the loop rule, which states that all potential differences in the circuit must sum to 0. And here's a potential difference graph over the different components of the circuit. So in this system, we have the ammeter in parallel with the second resistor, and this means that the current increases from 0.02 amps to 0.06 amps, and this is because the ammeter acts as a wire with no resistance, meaning that all the electrons will travel through the ammeter and none of them will travel through the 100 ohm resistor. And here's the measurements from the first circuit system, which are quite close to the actual values. And then here we have the RC circuit system, where there is a 9-volt battery, and then a light bulb of differing resistance, and then a capacitor of 0.2 farads. And we calculated the time, so the light bulb with 10 ohms, the charge time and discharge time are given, and then for a light bulb of 20 ohms, the charge time and discharge time are given as well. And those are the charge time discharge times of the capacitor. So in this one, the light bulb is 30 ohms, the battery is still 9 volts, and the ammeter is 0.2 farads. So I measured the voltage from the voltmeter at different times after removing the battery and completing the circuit, and then compiled this data into an Excel doc, which you can see right here. So you can see at the far left where it's the time versus the voltage, and then you can see the table in between the graph and the left, where I take the natural log of delta V divided by delta V initial. And this is because we can use the equation natural log of delta V over delta V initial equals -t over RC. We can use this to solve for the RC value of the circuit. So you can see I have plotted the graph in Excel of time versus the natural log of delta V over delta V initial. And this should yield a graph with slope -1 over RC. We get that from the equation above. So RC equals -1 over the slope. And then we get that the RC is equal to 5.998. And this is extremely close to the calculated theoretical RC of 6. So theoretical questions: what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulator? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? A real ammeter would have some small amount of resistance that would lower the magnitude of the current in the circuit. What if you're doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. So our ideal model would predict that the capacitor would be instantly charged fully if there's no resistor. In real life, this wouldn't happen because there's some small amount of resistance in the batteries and the wire that slow down the transfer of electrons.